Hello guys, how are you today? So today I'll be explaining I dropped my pen. The chapter 4 chemistry notes, but I'm only gonna be solving the questions. So let's start. Of course, if you see that the time on top is moving fast, it doesn't mean the video is moving. I pause from time to time to take some breaks and stuff like this, okay? So starting off in question 1, or not question 1, exercise 1. Now, personally, while I was reviewing this, I found this a bit confusing, but then I understood that it's a reverse reaction. Instead, the original reaction, if you know that iron, okay, its charge is 2 plus, so Fe2 plus Cu, we know the charge of Cu is 2 plus, so this is how it was originally. Then that means after it probably became Fe3 plus in addition to Cu plus. So what's happening over here is that Fe is losing an electron. Alright, so it's losing an electron, it's losing a negative charge, okay? That means the positive charge is increasing. And if you remember in the video before, or the chapter 4 summary video, we discussed and we said that oxidation is the loss of electrons. And what happened here? We lost an electron, so that means Fe underwent oxidation. It is oxidized. And again, we said that if something undergoes oxidation or is oxidized, then it is the reducing agent. So we can know that Fe became oxidized by two ways. Either you take the original equation and you see what were the changes that happened. In this case, it lost electrons. Okay, so that means it is oxidized, or you can go to the statement below where it says Fe3 plus is a reducing agent. Reducing agent means that it was oxidized. Now, what about this one? Cu2 plus was originally 2 positive, then it became 1 positive. That means it gained an electron, so gain of electron. That means it went under reduction, so it was reduced. So Cu2 plus was reduced. In other terms, it is the oxidizing agent. So for exercise 1, there are many ways to find out what the answer is. You can either do it like this, or you can directly go to the statement below. Fe3 plus is a reducing agent. That means it was oxidized. Then Cu plus is the oxidizing agent. That means it was reduced. And very simply, you found your answer to be C. Alright, now we move on to exercise 2. A spontaneous reaction occurs when a piece of iron, Fe, is placed in 1 molarity CuSO4. The reducing agent is. So let us take it like this. A piece of iron, Fe, okay, we added it to CuSO4. Now they are asking for the reducing agent. Here, this becomes really nice. So a spontaneous reaction occurs. If you remember from the Fickel-Brie reactions, a spontaneous reaction was like, for example, if we are talking Cl2 in addition to NaBr, okay, a spontaneous reaction will occur and then it becomes Br2 plus NaCl. This is the definition of a spontaneous reaction. So if they're talking about a spontaneous reaction, in this case, it means that it was Fe plus CuSO4. It's then gonna become Cu plus FeSO4. Now, how do we know which one is the reducing agent and which one is the oxidizing agent? Very simply, we're gonna talk about the oxidation number. So for Fe, we know since it is an element by itself, it's in the elementary state, then the oxidation number is 0. For Cu, in this case, we have to remember it is 2 plus the oxidation number, and for SO4, it is 2 minus. Now, if we go back here, Cu, it is an element in itself, so that means the oxidation number is 0. Fe became 2 plus, and SO4 is still 2 minus. So the only things that changed are Fe and Cu. So if Fe was 0, then it became plus 2. That means it lost electrons. So loss of electrons. So that means it was oxidized, because oxidization means a loss of electrons. So technically it is the reducing agent. Alright, because anything that undergoes oxidization is the reducing agent, and anything that undergoes reduction is the oxidizing agent. So very simply, for exercise 2, our answer is going to be A. The reducing agent is Fe, iron. Alright, so now we move on to CQD number 10. Find the oxidation number of each element in the following species. So let's start with A. NH3. We know H, the oxidation number of H is usually plus 1. But since there is a 3, okay, that is a coefficient, and not a coefficient, I forgot what you call this, but the number below, let's just say the number below, it is the number below, that means we have to multiply the oxidation number 1 by 3. So now it becomes plus 3. Now, the charge of NH3 in total is 0, so the charge of N, which we will call X, plus 3 is equal to 0. That means the oxidization number of N in this case is minus 3. But pay attention, did they ask us for the charge of H3 or the element? They asked us for not the charge, the oxidation number. Did they ask us for the oxidation number of H3 or the element H? They asked us for the element H. So for the element N, its oxidation number is minus 3, and for the element H, its oxidation number is plus 1. And that is it for part A. For part B, we're going to apply the same process, H2CO3. Its charge is 0. So we know H has a charge of, an oxidation number of plus 1, so plus 1 times 2, plus the oxidation number of C, which we will label X, plus the oxidation number of oxygen, in this case, which is going to be negative 2 multiplied by 3, is equal to 0. So 2 plus X minus 6 is equal to 0. Move it to the other side. We're going to get that X is equal to 4. So now the oxidation number for each element, for H it is 1, for C it is 4, and then for O it is minus 2. Now part C is tricky because it is I2, it is an element itself, so definitely the oxidation number of an element is 0. Alright, moving on to part D, MnO4 minus. Mn, we don't know its oxidation number, it's gonna be X. O is minus 2, so plus minus 2 times this number over here, which is 4. It is equal to minus 1 because this is the charge. So that means X minus 8 is equal to minus 1. Move minus 8 to the other side. X is equal to 7. So oxidation number of Mn is 7. Of O, oxygen is minus 2. Now finally for the Cr2O7, 2 minus. Very simply, Cr2O7, 2 minus. We don't know Cr, so it's going to be X. But since there is a 2, it becomes 2x. In addition, 2 minus 2 times 7 is equal to minus 2. So 2x minus 14 is equal to minus 2. Bring minus 14 to the other side. 2x is equal to 12. X is then equal to 6. So oxidation number of Cr is 6. And oxidation number of O is minus 2. And that's it for CQD number 10. Moving on to CQD number 19. Alright, we can read up just point number 16 because it's important for CQD number 19. For some reactions, a change in color can also identify redox reactions. For example, whenever a reaction involves acidified aqueous potassium manganate, which is purple, okay, it then turns colorless. Then, whenever a reaction involves aqueous potassium iodide, which is colorless, it will turn brown. So this is all we need to know. So acidified potassium manganate, it changes from purple to colorless. When acidified potassium iodide solution, which is a reducing agent, is added to an oxidizing agent such as chlorine or hydrogen peroxide, it turns from a colorless solution, they didn't state it's colorless, but usually it's colorless solution, to a brown color. Alright, so now we move on to CQD number 1. This is a nice question. They told us which of the following equations is an oxidation reduction or redox reaction. How do we know if something is redox or not? Very simply, there is many ways. I'm gonna teach you 2 ways, okay? I'm gonna start off with a complicated way for the first one, and then the easier way for the second one. Alright, so for the first one, we need to find the oxidation number of each one. So in this case, it's gonna be 2, 4, 2 plus 4 plus minus 6. Then here, Cu, its oxidation number stays as 2, so nothing changed, which means that's good. Oxygen is minus 2 plus carbon, which stays as 4, and minus 4 over here. So in total for oxygen, the oxidation number is minus 6. So by finding the oxidation number, we found that, okay, for copper, it's the same in the beginning and the end. For carbon, it's the same in the beginning and the end. And for oxygen, it's the same in the beginning and the end. So that means it is not a redox reaction, because a redox reaction is a reaction in which oxidation and reduction occurs. Now for the second one, which in my opinion is easier, is to scan through it and see if there is any single elements. So in this case, there is no single element, so probably there is no oxidation redox reaction. And to prove it even more, we can use the first way, in which we find the oxidation number. So this one, it's gonna be plus 2, minus 2. Then you do not consider the coefficients. You never consider the coefficients when doing the oxidation number. Plus 1, minus 1. Then here Zn stayed as plus 2. Then Cl became, it stays as minus 1, but this is times 2. So you can either do this one 2, so 2 times 1, so this becomes plus 2. Then 2 times minus 1, so it becomes minus 2. So here then this would follow, so minus 1 times 2, this becomes minus 2. And then finally over here it becomes plus 1 times 2, so plus 2, and then minus 2. So if you noticed, Zn started with 2 and it ended with 2. Oxygen started with minus 2, it ended with minus 2. Then it depends whether you want to consider the coefficient or not. If you do not consider the coefficient, then do not consider this, okay? But it's totally up to you. Since I considered the coefficient, I'm gonna continue by considering the coefficient. But anyways, in this case, the H started with plus 2 and it finished with plus 2, and the Cl started with minus 2 and it finished with minus 2. That proves that it is not a redox reaction. If we move on to the next one, we can see that we started off with elements and then it became a compound. So definitely there was a redox reaction. You can do it like this, but if you want to verify it even more, you can apply the oxidation number rule. So if you want to use the coefficients, in this case it's going to be 2 times plus, for the elements it's 0 plus another element, it becomes 0, will give us 2 times the oxidation number of Cu, which is plus 2, and then 2 times the oxidation of oxygen, which is minus 2. So as you see, it becomes plus 4 and minus 4, which even if you add them, they give you 0. What matters is that each element, it gained and lost electrons. That means oxidation occurred when you lost electrons and reduction occurred when you gained electrons. So yes, it is a redox reaction. Now finally for the last one, I'm gonna do it quickly by the oxidation number because more practice for us. Okay, so in this case we have Na2CO3. So Na2 is 2 times plus 1, C is plus 4, O3 is minus 2 times 3. Then 2HCl becomes 2 times plus 1, 2 times minus 1. 2NaCl is also 2 times plus 1, 2 times minus 1. Then H2O is 2 times plus 1, and then the oxygen is minus 2. The carbon is 4, and then the oxygen is 2 times minus 2. So if you put it all together, if you see, for example, each one by itself, Na, it's 2 times plus 1, Na is also 2 times plus 1. And if you check them each one by themselves, you will see that each element has the same number of electrons in the start and in the end, which means a redox reaction did not occur. So for CQD number 1, C is our answer. Now exercise number 6, since it's not that important, I'm going to scan through it quickly. I'm going to use the other way, which is to see if we have elements and compounds or not. Except for the first question, because for the first question I find it really interesting and I prefer that we use the oxidation number method for the first question. So starting off for part A, we have plus 1 in the H, minus 1 for the Cl, then plus 2 for the H2, minus 2 for the oxygen. It will now give us plus 3 in the H, however, minus 2 in the oxygen, and if you add 3 minus 2, you're going to get plus 1. That's why the charge is positive 1. In addition to minus 1, which is the oxidation number of Cl minus. Now pay attention, Cl minus is an ion, not an element. Alright, so if you look at it really carefully, we will see for hydrogen we have 3 and we ended up with 3. For Cl we have minus 1, we ended up with minus 1. And for oxygen we have minus 2 and we ended up with minus 2. Now for the rest, I'm going to use the if we have an element and compound or not. So starting off with the part B, we have an element and then it gets put into a compound. So whenever we have an element that is put into a compound, then definitely there is a redox reaction. Here we have O2, which is our element, and it was put into a compound, which is 2H2O, so yes, it is a redox. Then we have 2Fe2O3, and then carbon, which is our element, and it was put into a compound, so definitely yes, it is a redox. And then for part E, we have 2HCl plus Zn. Zn is our element, and it is put into a compound, so yes. And then finally, we don't have any element that was put into a compound, so for part F, no, it is not a redox. If you guys want to check on the internet, and in my opinion, B, C, D, and E are redox equations, so these 4. And that is it for exercise 3. Now we move on to the next one, which is CQD 11. So for CQD number 11, we have the electrolysis of molten lead bromide, PbBr2, is conducted using the below apparatus. Now for part A, they asked us to write the half reaction that takes place at the negative electrode, and part B, they asked at the positive electrode. So the positive electrode is the anode, the negative electrode is the cathode. What we need to know is that they put it in molten, so molten is very important. What happens in molten is that in the positive electrode, the anions are gonna form, and in the negative electrode, the cations are gonna form. So in this case, our equation is PbBr2. Now, if you split them into cation and anion, you are gonna get Pb2 plus and then Br minus, or 2Br minus. Now what's gonna happen is the anion, which is the negative ion, will go to the anode. and the cation, which is the positive ion, will go to the cathode. This is only the case in the molten. For aqueous, we will discuss a set of rules I will talk about later when we reach aqueous and dilute and whatnot. So the half reaction that takes place at the cathode is gonna be Pb 2 plus, okay, in addition to 2 electrons, okay, the 2 electrons are gonna replace the missing electrons, okay, so 2 minus is gonna counteract the 2 plus, and that is gonna give us Pb. This is for part A. For part B, we're gonna discuss the half reaction that takes place at the positive electrode, which is the anode. At the anode, what happens? The anion goes, our anion is 2Br minus, and it's gonna become Br2, but it's gonna release 2 electrons, so 2E minus. Alright, and now if we write the full equation for the electrolysis of molten lead bromide, okay, it's gonna start as PbBr2. This is molten, so liquid PbBr2 is gonna give us Pb as a liquid in addition to bromine Br2, which is released as a gas. So that is it for CQD number 11. Exercise 4, what will be observed at each electrode when molten lead dibromide is electrolyzed. This is the same as we discussed previously in CQD number 11, parts A and B, because we discussed what happens at each electrode. Now let us discuss what happens at each electrode in the ZnCl2. We will discuss what will happen at the anode and at the cathode. At the cathode, the cation is gonna go. Our cation in this case is Zn2 plus, and our anion is 2Cl minus. So at the cathode, what's gonna happen is our Zn2 plus is gonna go. And then, since we're talking about molten, 2 electrons are gonna balance it to form Zn as a liquid, okay? Then in our anode, we are gonna have our anion, which is 2Cl minus. It is gonna become Cl2 gas, but it is gonna release 2 electrons in the process. And that is pretty much it for exercise 5. Now moving on to the next exercise, we have CQD number 13. Now here we are talking about concentrated hydrochloric acid, HCl. Is electrolyzed using the apparatus below. Now let me write something. We have what happens at the anode and what happens at the cathode. This we have to pay attention. Is it concentrated or is it dilute? If it's molten, it's a whole other story. If it's molten, the anion will go to the anode and the cation will go to the cathode. But if it's concentrated and dilute, this is a different thing. So let us say we are talking about concentrated. At the anode, if we are talking about I minus, Br minus, or Cl minus, these will form. Otherwise, OH minus is gonna form. Whereas at the cathode, if we are dealing with these specific metals, which are Cu plus and Ag plus, now pay attention, there is Cu2 plus and there is Cu plus. There is a difference between these two. Here we are discussing Cu plus. So if we have in the cathode and it is concentrated Cu plus and Ag plus, then they will form, or in other terms, they will discharge, or else hydrogen will discharge, okay? These are the only things. So if you get anything else than I minus, Br minus, Cl minus, then OH minus is gonna form. If you get any other metal than Cu plus and Ag plus, then H plus is gonna form instead of it. However, if we are talking about dilute, in dilute at the anode, the only thing that's gonna form is OH minus, and at the cathode, the only thing that is gonna form is H plus. That's pretty much it, okay? So, label on the diagram the position of the electrodes. We said the positive side is the anode, so A, and then the negative side is the cathode, so C. What are the two observations that we can observe when the switch is on? When the switch turns on, definitely the light bulb is gonna light up, so light bulb lights up. Another thing is probably that bubbles are gonna form, so effervescence. Now, we are discussing hydrochloric acid, which is HCl. Now, they're telling us, give the name of the product at the positive electrode. So what will form at the anode? Definitely Cl- is gonna form, but it will not form as Cl-. Instead, it will form as chlorine gas, which is Cl2 gas. So chlorine gas is gonna form at the positive side, which is the anion. Now they told us give a test to identify the product formed at the positive electrode. This we should know from before, that to test chlorine gas we use the litmus paper and it will bleach litmus paper. So litmus bleaches. And that is it for CQD number 13. CQD number 14. Which of the following aqueous solutions produces H2 gas and O2 during electrolysis? Here they were I don't know by accident or on purpose, but they gave us what each one forms at the anode and the cathode. So they're telling us which one forms H2 and O2. Let us find. It is actually only E. It's the only one that forms H2 and O2. If you want to know which one forms at which, first thing you need to know is that for sure, okay, if we have aqueous, okay, first thing we need to know, is it aqueous or not? So C is molten, we don't choose it. Second thing we need to know, is it concentrated or not? They did not give us that information, so we're just going to assume that everything is concentrated. Since it is concentrated, then K is not going to form, instead I will form. Cu and I is going to form. Cu is going to form, but SO4 is not going to form. But here, K will not form and SO4 is not going to form. So instead, O2 will form at the anode and H2 will form at the cathode. O2 will form instead of OH minus and H2 will form instead of H plus. Alright, so now we move on to CQD number 18. Here they told us, fill the table with the correct products formed when aqueous copper sulfate solution is electrolyzed using graphite and or copper. Here's the thing, when we are using electrolytes, the electrodes are supposed to be inert. Inert, for example, in statement number 22, they can be carbon or platinum. Inert means they do not have a charge, so they will not react with the others. However, if we used copper or anything that is not inert, what will form at the anode and what will form at the cathode? Very simply, if we used copper electrodes, copper itself is going to form at the anode and at the cathode. If we used any other type of metal, for example, if we used sodium as the electrodes, then at the anode sodium will form and at the cathode sodium will form. Same thing. If you use anything that is not inert, however, if you use carbon, which is graphite is carbon, or platinum, what will form at the anode will be based on this solution. So in this solution, we are talking about copper sulfate, so CuSO4. We know copper is gonna form because it is one of the things that are gonna form. And because copper is a cation, it's gonna form at the cathode, so copper is gonna form at the cathode, if we're talking about graphite. However, SO4 is weak, it's not gonna form at the anode. Instead, what will form? Oxygen gas will form. Alright? So now let us move on to exercise 6. Here we have the table. The following, are results for the experiments on electrolysis using inert electrodes. Complete the table below. The first one has been done for you. So first thing we are gonna see is that the change at the negative electrode. First of all, we have the electrolyte, the change at the negative electrode. Here, this means the solution. So let's say instead of electrolyte, solution. Then the change at the positive electrode, and then the change to electrolyte. For the first one, we have potassium formed, which is quite unusual because potassium will not form unless it is molten. So that directly gives us a clue that it is molten. That means our cation, because it forms at the negative electrode, which is the cathode, and the positive, which is the anode. So it will form at the negative electrode, so it is the cation. So potassium is our cation, so K. And then at the positive electrode, we have iodine, so Ki. So molten Ki, or molten potassium iodide. And because it is molten, it will be used up. Next one, we have dilute aqueous sodium chloride. Whenever it is dilute at the cathode, what's gonna form is hydrogen. I forgot how to spell, sorry, hydrogen. And because it is dilute, what will form at the anode is oxygen. Now here is a trick. The whole purpose of electrolysis is to separate. So if we have dilute aqueous sodium chloride, NaCl, the whole purpose of this is to separate the two of them. But definitely Cl is way stronger than Na, because if you remember the table, let's say it was not dilute, instead it was concentrated. Na would not form either way, but Cl would definitely form. So that means Cl is way stronger. So what's gonna happen is that Cl, let's say this over here is the anode and this over here is the cathode. Cl would exist over here. It's trying to come. But what forms instead at the anode is oxygen, or OH minus, because it is stronger. But during that time, what happens is that the remaining OH minus in the water would have bonded with the Na, so the Na plus, so it will form NaOH. So I think I would prefer if I drew a diagram. Okay, we have here the anode, here the cathode, and here this is a battery, let's say. Okay, and let us imagine that we are putting in this dilute solution of sodium chloride, which is NaCl. What's gonna happen is that we're gonna have Na everywhere, Na, and then Cl. But since it's dilute and aqueous, that means it's put in water. So we have also H2O molecules, which will also form OH minus, and then H plus, and basically like this. And as we discussed, the Na is really weak, so either way it's not gonna go to the cathode. What will go instead is the H plus, so the H plus will go to the cathode directly. However, Cl minus is really strong, so it will want to go to the anode. But what will come before, what is way stronger than the Cl minus, if it is dilute, it is the OH minus, so the OH minus will come before. But by the time that the Cl is coming here, so that it is it's trying to join in the anode, it's not able to, so it will go back to try and join with the Na, but instead the Na would have already joined with the remaining OH, so we are left with an AOH. So here this was molten Ki, here this was hydrogen, oxygen, and then it will form an AOH. Now finally, for the last one, we have hydrogen is formed, okay, which means it could be dilute and it could be concentrated. We don't know. Then we come here, bromine is formed. Directly from the bromine, we know that it is concentrated. And we know that our anion is Br2. Then we move to the change in electrolyte. We have potassium hydroxide is formed. Where did the potassium come from? It came from here, so KBr2. Or in words, it's potassium bromide. And that's it for exercise 6. If we move on to CQD number 12, let us just fill in the blanks based on what we know. So concentrated solution of sodium bromide, we know bromide is strong, so at the anode bromide is gonna form. Whereas at the anode, we know Na is weak, it's not gonna form. Instead, hydrogen will form. Concentrated again, solution of AgNO3. Ag is strong, so it's gonna form over here, whereas NO3 is weak, so oxygen is gonna form instead. Now, whenever you see dilute, we should know that at the cathode, hydrogen is gonna form directly, and at the anode, oxygen is gonna form directly. And that's pretty much it for CQD number 12. Moving on to CQD number 15. We have an iron spoon to be plated with copper metal. So iron is Fe and copper is Cu. We need to write the two half reactions that occur at each electrode. So in each electrode, so let's say here's the anode and here is the cathode. So what's gonna happen is that at the cathode, the cations are gonna be attracted. So let's say we have Cu2 plus and Cu. The Cu is gonna go to the anode, so it can give an electron. Okay, so the Cu will go to the anode, and then the equation becomes Cu solid will become Cu2 plus, okay, in addition to 2 electrons. So it goes to the anode to give electrons, whereas the Cu2 plus will go to the cathode to gain electrons. So the equation becomes Cu2 plus aqueous in addition to 2 electrons will give us Cu solid. So very simply, what we need to understand is that we know that first of all the anode is the positive side and the cathode is the negative side. So what's happening here is that the Cu solid is gonna go to the anode, okay, it's gonna be attracted to the anode because this is positively charged, and it's gonna give it some of its electrons, and then it becomes Cu2 plus. And what happens is that this Cu2 plus, okay, let's say it's the Cu2 plus that forms from this, if you want to make it more interesting, the Cu2 plus that will form from this is gonna move and be attracted to the cathode, which is negatively charged, and from it, it is gonna gain 2 electrons, so then it becomes neutral again, and then the process repeats itself, and this is how the plating works. Alright, so that's CQD number 15 done. Moving on to CQD number 16. Now for number 16, which of the following apparatus could be used to electroplate an iron nail with a nickel? What we need to know is that the thing to be electroplated, or the thing to be plated, is placed at the cathode, whereas the object to plate with, which in this case is the nickel, is placed in the anode. So here, the cathode we know is placed at the negative side, so negative is the cathode, this is correct. And then the positive side is gonna be the metal to plate with, which is in this case correct. But that's not our only condition. We also have to check the electrolyte solution. In this case, it's aqueous nickel sulfate, which is correct because the solution has to be made out of the metal that we are plating with. In this case, it is nickel. So part A works. If you check the rest, they are all incorrect. So that means our only correct answer is A. Moving on to our next question, which is CQD 17. Hydrogen fuel cells may be used to replace combustion engines in a car. Give the reactants involved in the reaction occurring inside of a hydrogen fuel cell. So what exactly happens in a hydrogen fuel cell? We have the reactants that happen or that react in the hydrogen fuel cell are by the name hydrogen, and another one is oxygen, and they are both gases, so hydrogen gas and oxygen gas. Now, what exactly happens is this chemical equation that we will put now. The chemical equation is 2 hydrogen gas, so 2H2, in addition to oxygen, O2, will give us 2H2O, water. So this is a hydrogen fuel cell. It's an eco-friendly, way to form fuel. It will replace combustion, and it's formed out of hydrogen gas and oxygen gas, and then it forms water. So this over here is part A, this over here is part B. Now part C. What are the advantages of hydrogen fuel cells or hydrogen oxygen fuel cells? They produce only water, so product is only water and no CO2 emission. You can say also environmentally friendly. And that is it for number 17. Now we move on to CQD 21. Which of the following electrolyte cells form gases at both of its inert electrodes? We need to know which ones form gases. Definitely molten will not form any gases. So cell D and E will not form gases. So now we look into the remaining. So we are left with A, B, and C, cell 1, 2, and 3. They are all aqueous, so this is a good thing. Then for cell 1, there is sodium iodide. Sodium will definitely not form. Instead, what will form is hydrogen, so this is a gas. But iodide is formed as a solid. So solid iodide, we are not looking for a solid. We need gases at both of the inert electrodes. So definitely it's not gonna form. The next one, we have copper sulfate. Copper is going to form as a metal. Directly, we do not choose it because metal is a solid. And now finally, the last one, which is cell number 3, we have sodium, which will form hydrogen, so H2 gas, plus chloride, which will form Cl2 gas. So that means in number C, not number C, oh my goodness, letter C, cell number 3, aqueous sodium chloride, it will form gases at both of its electrodes. Okay, for CQD number 22, which of the following represents a reduction change? So we need to notice reduction. Here Fe became Fe2+. This is oxidation because there is a loss of electrons. Here we have to pay attention because it is a peroxide, and we said when there is peroxides with oxygen, the oxidation number changes, so it was originally 2 times plus 1 plus 2 times minus 1. So when we're talking about peroxides, the oxidation number of oxygen is -1. Will then give us H2O. So 2 times plus 1 times -2. So we could do it like this. Okay, and then we could talk about the state of oxygen in each one. So oxygen over here, the oxidation number is -1, whereas over here it becomes -2. So there is a gain of electrons, and a gain of electrons means there is a reduction change. Moving on to the last one, Cr2O4 2- gives us Cr2O7 2-. Solving it, we are gonna get, so let me just clear it out. Here the oxidation number is 3 times 2 plus -2 times 4 is equal to -2. And then here the oxidation number is 3 times 2 plus -2 times 7 is equal to -2. So this is wrong. So that means this is not 3. Instead, this becomes 6. Or instead, this is the opposite. So the oxidation number is no longer 3 for Cr, but then it becomes 6. So that means it's increasing. That means it's what? It's losing electrons. And if it's losing electrons, then it's definitely oxidation. And we do not need oxidation as we are only looking for reduction. So the only one that has reduction is 2. So our answer is 2 only. Moving on to question number 23. A student assembled the following electrochemical cell. What is the direction of electron flow in the electrochemical cell? It is, so this question is a bit difficult. We need to look at the electron potentials. So very simply, by the electron potentials, we know that Zn has a smaller electron potential than Fe, so then definitely it's gonna flow from Zn to Fe. Alright, this will probably be given to us in the exam, hopefully. Now what's the, we already did part I. Part 2, the voltmeter reading change. Describe the change and explain, and oh my goodness, I'm so sorry. I don't know why I'm not able to read today. Describe the change and explain why this change occurred. So they replaced the Fe with a silver Ag electrode. The voltmeter reading changed. So again, looking at the electron potentials, we know that the electron potential of Ag is definitely like the difference between the electron potential in Ag and Zn, and Fe and Zn is way higher, so that's why there is a change in the voltmeter reading. Now, number 3, when the student replaced the zinc electrode with a copper electrode, the voltmeter gave a negative reading. Why? Because usually copper has a smaller electron potential than Fe. Or in another sense, it is less reactive than Fe. So we move on to part B. A student conducts electrolysis of concentrated aqueous solution of sodium chloride using the following apparatus. They're telling us which particles allows the flow of the electric current in the sodium chloride solution. It's definitely the Na plus and the Cl minus, because without them there would be no flow, because the Na plus is attracted to the cation, or the cathode, sorry, and the Cl minus is attracted to the anode, and without them there would be no flow. Now, give 2 reasons for the use of graphite, because graphite is inert and it also conducts electricity. Even though it's inert, it will not react. It doesn't have a charge, but it does conduct electricity. What is the gas produced at the anode? We know that we are talking about concentrated aqueous solution of NaCl. Na is not going to form. Instead, what is going to form is that hydrogen H2 gas is going to form. However, Cl2 gas is also going to form. So the gas produced at the anode is chlorine gas. Write the ionic half equation for the reaction occurring at the anode. Very simply, it is 2Cl minus will give us Cl2 gas plus 2 electrons. Alright, so now V, a blue litmus paper is dipped into the remaining solution after electrolysis is over. Does blue litmus paper change color? Explain why. Now, I explained above why it becomes NaOH. So let us stay on the fact that it is NaOH. Okay, they told us, does the blue litmus paper change color? We know NaOH is a base, and it's not only a base, it's a strong base. But will it change the blue litmus paper? No, it will not. It will change red litmus paper to blue, but blue litmus paper, it will not change it because it is a base. CQD number 24. Let me just check how more we have. 25, 26, and 27. I believe I'll do them, so let us do it. Electrolysis is used to break down ionic compounds. A student conducts an electrolysis for a concentrated solution of copper chloride. Why is it recommended to use inert electrodes in electrolysis to prevent any unwanted side reaction with the solution? So we don't want any extra reaction with the solution. That's why we use inert. They do not react with anything. They do not have a charge. Okay, a solid deposit is observed at the negative electrode. Identify the solid. What did we put? We put concentrated copper chloride. So Cu, Cl2. Oh, but now we know that Cu is strong and also Cl2 is strong. So what's gonna form is, since they are both concentrated, Cu metal is gonna form, so copper metal will form, and Cl2 gas is also gonna form. So at the negative electrode, which is the cathode, where the cation will form, we will see that copper formed. Now the ionic equation for this is Cu2 plus 2E minus gives us Cu. Basically, what we need to remember is that at the anode, what happens is that X2 plus, it's not an actual element, I'm just naming it X. So X2 plus, let's say as an example, will give, or my apologies, not X2 plus, X is gonna give us X2 plus 2E minus. This happens at the anode. Whereas at the cathode, what happens is that X2 plus 2E minus will give us X. This is how it goes. Now in IV, they're asking us, a fizzing is observed at the positive electrode, which is the anode. The gas released is chlorine gas, and it forms since the chlorine is discharged. Because at the anode, oxidation always happens. Now part V, identify the species that's reduced in the solution undergoing electrolysis. Very simply, we know that at the cathode, where the metals are, they all get reduced. So that's pretty much it for part A. Moving on to part B, a student wants to electroplate an iron rod with chromium. At which electrode should the student place the chromium rod? We said that if we are plating with something, the object to be plated with is placed at the anode. Now suggest a suitable electrolyte for this electrolysis. Of course, it has to be made out of the metal we are plating with. So let's say the electrolyte is going to be chromium solution, anything that's aqueous. So for example, chromium nitrate. So CrNO33. So something like this. Now we need to write the half equation. So this is the half equation. Now at which electrode does oxidation occur? We know that oxidation always occurs at the anode, whereas reduction occurs at the cathode. Now give a reason why chromium is used in electroplating, because two reasons is that it's decorative, it's very good for decoration, and it also protects it from corrosion. And that's it for CQD24. Now moving on to CQD25. A student conducts electrolysis on dilute solution of sodium chloride, so NaCl. Definitely what's going to happen is that Na, instead of Na, what will form is H+, it will form at the cathode, whereas Cl is going to form OH-. This is only the case because it is dilute and it will form at the anode. So gas X makes a pop sound. Always remember, pop sound when tested with a lighted splint is hydrogen. Okay, if it relights a splint, then it is oxygen. Now suggest a test for oxygen gas. Approach a glowing splint and it will relight it. Suggest a material to be used as an electrode. Let us say, for example, carbon or graphite or anything that is inert. So for the electrodes, they have to be inert and they conduct electricity. That is it for CQD25. Moving on to CQD number 26. Now here this is interesting. We have molten lead bromide. Molten lead bromide means that at the cathode they are gonna form Pb2+, or not Pb2+, Pb they will form. And at the other one, what's it called? The anode, they are gonna form Br2 bromine gas. So this process is called electrolysis in the figure. What are the expected observations on the positive electrode and negative electrode? On the positive electrode, there will be a brown gas, which is the Br2 gas, the bromine gas. And at the negative cathode, there is, electrode, which is the cathode, there will be a silvery substance, which is lead. Now, a Bunsen burner is used to melt solid lead bromide. How can the student adjust the Bunsen burner to give the hottest flame? This is something we took last year, the first section. We need to open the air hole. Part D, why is it recommended to use graphite electrodes? Because they are inert and they allow electricity to pass through, so they are electric conductors. When replacing molten lead bromide with an aqueous solution of lead bromide, so they replaced molten with aqueous solution. What's gonna happen is that Pb is weak, so it's not gonna form Pb. Instead, hydrogen is gonna form, and the Br2 is also gonna form. So they're asking us to suggest a test for hydrogen. Maybe you should approach a lighted splint and it will form a pop sound. Now, how can you identify bromine gas? Bromine gas is brown in color, and that's how you identify it. Now, the last question, F. Lead bromide is classified as hazardous chemical. So just a safety precaution when dealing with lead bromide. Either wear gloves or goggles, and that's it for CQD 26. Now the last CQD, and we are done for this chapter. Okay, here we have an experiment B, C, okay. Here is A. The burette showed the following measurements. They want us to record the final burette reading. So we just need to record this reading. As you can see, it's upside down. So 16, that means 16.1, 0.2, 0.3, 0.4, 0.5, 0.6. So the reading is 16.6 centimeter cube. Then the volume of potassium manganate solution used in centimeter cube. So if we go up and see what they did, they added it to this flask. So what's gonna happen is, since they added it to this flask, it's gonna take the volume of the liquid in the flask. So it's gonna be 16.6 centimeter cubed. Now B, they told us record the final readings in centimeter cube. So we have the initial and final. The final is 38.6 centimeter cube. Now calculate the volume of potassium manganate solution that was used in this experiment. So this experiment is different from the one above. Very simply, we just need to subtract 38.6 minus the initial one, which was approximately 10.4. So 38.6 minus 10.4 is going to give us 28.2 centimeter cube. Now they asked us, which solution is more concentrated? Solution R or solution T? This is solution T, and this over here is solution R. Now definitely solution T is the more concentrated because it had a bigger volume of potassium manganate. Now if in experiment 2 the student used 50 centimeter cubed of solution T instead of 25 centimeter cubed, calculate the volume of potassium manganate needed to reach the end point. So very simply what was done was that they doubled it. So what we're gonna do is we're gonna double our answer. We got 28.2 as our volume of potassium manganate. We're gonna double it, so multiply it by 2, and we are gonna get 56.4 centimeter cubed. Now part E, another student conducted the same experiments using a measuring cylinder to measure 25 centimeter cubed of solutions R and T instead of a pipette. Now they told us how would his results differ from that of the student who used the measuring cylinder. Definitely the measuring cylinder does not take as much time as the pipette, but the pipette is more accurate. Now for part F, how can the student reach more reliable results in this experiment? Maybe repetition. The only thing you need to do is repetition. That's why in many cases, especially in biology and chemistry, when they tell us to plot a test, we have 6 points. Okay, first thing we need to state the independent variable, the dependent variable, and then our variable. And then we state that I repeat this solution many times, like the repetition, and then the safety, and then you conduct the experiment. This is how you do the, especially in the mocks and in the IGCSEs for the people who are doing it. Alright, so now we move on to G. Indicators are used in most titrations to determine the end, when the endpoint is reached. Why no indicator was used in this titration? Because we know that potassium manganate already changes color at the end point. Because potassium manganate is a substance that does change its color. It's not any random substance, it's one that changes its color. That's why they did not use a titration. So thank you guys for watching. The rest of it, I'm not gonna do it because this, I believe you're supposed to do it by yourself as extra practice. But anyways, I hope you do well in your periodics and have a lovely back to school.